Hey, welcome back to the Meat Star. Today we're going to be talking about PID, pellet grill controls. So basically, a PID is a controller that controls your temperature of your grill. Let's get into it. Here you see the 4 things that any controller must do. It must measure, or any control system, I should say. It must measure, it must compare, it must compute, and correct. I commonly like to call this the MCCC. Measuring. Measuring is done by the transmitter thermocouple, or RTD. It measures the output of the process. The output of the whole process, if you look over here at your grill, at the very top, is your grill temp. That's what we want to maintain. You want to maintain your grill temp inside your smoker. So your grill temp, through the thermocouple, it takes that signal and sends it to your computer or to your controller. Now here's where the comparing and computing is done inside of the controller. It compares the incoming, which is the actual signal or value, with the set point, which is the desired signal of the controller. And excuse me. And then the PID function is applied. Now we're going to go over and talk about each function of the PID in a little bit. But okay, as you look over at your Traeger controller, which I got here, you have your process variable and you have your set point. Your process variable is basically telling the controller, this is what I got, and the set point is telling you, hey, this is what I got. And through the PID function, it sends out a signal which corresponds to the correct direction to bring your error to 0 and then stable out at your new set point. As you look here, the correction is done in the final control elements. In your grill, your final control elements are your combustion fan, as you can see here, and it's also in your auger motor. Now, as we get a signal to come up in to a set point, your auger fan is going to start turning, which is going to then apply more pellets into your fire pot. Also, in turn, to have that perfect combustion, your combustion fan is also going to kick in. And as it kicks in, it creates more heat, your grill temp goes up, and the same process happens over and over again. But everything is done in this right here is done through the PID function. Let's take a look at it right here. Here, P, which stands for proportional. Term P is proportional to the current value of the set point minus the process variable. As you look over down here, you'll see your set point, which is at 250, and your process variable is 125. An example, if the error is large and positive, the control output will be proportional large and positive, taking into account the gain factor K. Now we're not going to get into talking about the gain factor, because the gain factor, you're going into your controller tuning. Your controller, when you get a controller from any manufacturer, it is automatically tuned, which is your gain setting. Your gain setting is no more than, it's a setting in your controller that you go in and then you make your controller react faster or slower. But we're not going to get into that. We're just going to talk about the 3 functions that it does. Using proportional control alone will result in an error between the set point and the actual process variable, because it requires an error to generate a proportional response. If there is no error, there is no corrective response. If we just had a controller that was proportional, it would take us from, if you see here, we got 125 as a process variable, and we got 250 here. If you follow that red line, it goes up and then it settles out right beneath the set point. And here you have your offset. And a proportional control, that's the function. If you got a controller that's just proportional, that's what it's going to do. When it first notices that there is a offset, it's first going to apply, look at the blue arrows, it's going to apply the big step, because it said, hey, 125 is what I got, 250 is what I need. So it's going to provide that big step. And as it slowly gets closer to the set point, it gets smaller and it gets smaller. So basically, the PID function, the P function in PID takes an error between your process variable and your set point, whether it be increase or decrease, because sometimes you may want to go down, and it's going to take it, it's going to go proportional to the amount of error. Now let's look at D. Now we skipped I because I think D should come before the I. Now term D is best estimate of the future trend of your SP and PV error based on the current rate of change. It is sometimes called the anticipatory control, as it effectively seeking to reduce the effect of the SP and the PV error by exerting control influence generated by the rate of error change. The more rapid the change, the greater controlling or dampening effect. And that sounds like a whole bunch of mumbo jumbo, a whole bunch of $50 words that nobody really understands. But here, I'm gonna try to explain it to you. Once again, we got that offset, we got that process variable 125 at the bottom of the diagram, and we need to go to set point to 250. Now, if you follow the red line, those arrows just to the left of that red line, that's your proportional. That's your proportional action, the P. It says, hey, I gotta get up there, so it's getting up there. It's gonna get up there, and the closer as it gets to set point, it wants to stop. But it doesn't have the ability to just stop on a dime and go to 250. So what it does, it may overshoot because we have momentum from the process. What the derivative action does, it places a downward motion on the action. So as the proportional is getting smaller and we get above set point, the derivative kicks in and says, hey, we're above set point, and it says we need to go down, and then we'll get that swing and then we'll start to come down. And then soon we'll settle out just below the set point with proportional control. So basically what a derivative action does, it's a dampening effect. It dampens the output of your controller so you don't have such crazy swings. Now let's look at the I. The term I accounts for the past values of the SP, which is the set point, and the PV error, and integrates them over time to boost the I term. For example, if there's residual SP and PV error after application of the proportional control, the integral term seeks to eliminate and the residual error by adding control effect due to historical cumulative value of the error. When the error is eliminated, the integral term will cease to grow and then result in the proportional effect diminishing and the error decreasing. But this is compensated for by the growing integral effect. I know that's difficult to understand because it was difficult to read. Basically, what integral does, you remember here, when we went back to our first, look right here at the offset and think back to the first slide. And the first slide showed where the proportional would keep us. It would keep us right here. And with integral, what it does, it notices that offset, and we're never going to actually be on the set point. So the integral action slowly just adds a little bit. Say, hey, let's get back up to set point. And then it wastes a little bit of time, it adds a little bit more. Then it adds a little bit more until we're slowly, and then we get to our set point. I hope you guys got something out of this. Remember, it's the meat stall. Find you some meat and smoke it.
Okay. Turn me up a little bit.